Hello everyone and welcome back to the video lecture series for Calculus 1. Today we are going to be looking at limits at infinity. So with limits at infinity, they occur when the independent variable becomes infinitely large in magnitude, either positive or negative. So in other words, limits at infinity occur when x approaches positive infinity or x approaches negative infinity. It is asking what is the function doing as x grows arbitrarily large or arbitrarily small. So what limits at infinity determine is the end behavior of the function, because they describe what the function is doing at extreme values of x. Now, limits at infinity can be infinite, such as in the case of polynomials. So for this first example, we've got the function f of x equals x squared, and we're going to take the limit as x approaches infinity of f of x. So what this limit is asking is, what are the y-coordinates doing as x gets infinitely larger and larger? So as x gets larger and larger, you can see that the y-coordinates are also increasing without bound and without end, as demonstrated by this arrow here. So because the y-coordinates are increasing without bound as x grows infinitely large, we say that the limit as x approaches infinity of x squared is equal to positive infinity. Now for the next one, the limit as x approaches negative infinity, what this is asking is, as x grows arbitrarily small, or more and more into the negatives, what are the y-coordinates doing? Well, as x approaches negative infinity, the y-coordinates are still increasing forever and ever without bound. So the limit as x approaches negative infinity is also equal to positive infinity. Now for this next one, we're going to take the function f of x equals x cubed, and we're going to find the limit as x approaches infinity. So again, what this is asking is, as x grows infinitely large, what are the y-coordinates doing? Well, as x gets larger and larger, the y-coordinates are also growing larger and larger. So this limit is equal to infinity. Then, for the limit as x approaches negative infinity, you can see that the y-coordinates are decreasing forever and ever without bound. So this limit is equal to negative infinity. Now, not all limits at infinity are going to be infinite. So let's look at the function f of x equals 1 over x, the reciprocal function. And we're going to find the limit as x approaches infinity. So x here is this value in the denominator. And no matter what that value in the denominator is, no matter what you plug in for x, it will always have a 1 in the numerator. So as x gets larger and larger, as the denominator becomes larger and larger, what is happening to the overall fraction as the denominator becomes larger? Well, as the denominator becomes larger and larger, the overall fraction is actually going to get smaller and smaller. So the overall fraction is going to approach 0 as the denominator gets larger and larger, which you can see here from the graph. This graph is getting closer and closer to the x-axis, but it's never actually going to reach the x-axis, because the only way that a fraction can equal 0 is if the numerator equals 0, and that numerator is never going to equal 0 no matter what value you plug in for x. This overall fraction will get pretty close to 0. If you were to plug 10 million into that denominator, it's going to be a very small decimal, very close to 0, but it's not truly 0, and it's not exactly equal to 0. But a limit is asking what a function is approaching. Not necessarily will this function ever achieve a value of 0. So even though it will never achieve a true value of 0, it is approaching 0. It's at least heading towards 0. So we're going to say that the limit as x approaches infinity of this f of x is actually equal to 0, because that's what the y-coordinates are getting closer to, and that's what limits care about. Now, the same thing for the limit as x approaches negative infinity. Even though the fractions will be negative, the fractions are still getting smaller and smaller. This graph is still getting closer and closer to the x-axis. So that graph is approaching 0. These values are approaching 0. So the limit as x approaches negative infinity of 1 over x is equal to 0. Now, if you remember anything about the graph of 1 over x from previous courses, you might remember that this graph actually has a horizontal asymptote at the x-axis. The x-axis is also known as the line y equals 0. So this graph actually has a horizontal asymptote at y equals 0. And it's no accident that it has a horizontal asymptote at y equals 0, and each of these limits at infinity came out to 0. In fact, the definition of horizontal asymptotes actually involve limits at infinity. So again, definitely copy this one down. You're going to be using the definition of horizontal asymptotes a lot because horizontal asymptotes are actually closely linked to limits at infinity. So if f of x becomes arbitrarily close to some finite number L for all x's that are arbitrarily large, approaching infinity, then we say that the limit as x approaches infinity of f of x equals L. And if this limit as x approaches infinity equals a real number L, we say that the line y equals L is a horizontal asymptote for f of x. And it doesn't matter if you take the limit as x approaches positive infinity or negative infinity. The same thing will apply if the limit as x approaches negative infinity of f of x is equal to some finite number L. So in plain English, if you take an a limit at infinity and you end up with a real number, then the horizontal asymptote is y equals that number. So if you take the limit as x approaches positive infinity or negative infinity and you get a number, that number is your horizontal asymptote. Now, if you take a limit as x approaches infinity and you get positive or negative infinity, then that means there is no horizontal asymptote. So like in the case with these two polynomials here, these two polynomials did not have horizontal asymptotes, so each of the limits at infinity were themselves infinite and came out to infinity. Now we are going to be finding limits at infinity algebraically, and with direct substitution at infinity, well, technically it's not mathematically allowed because infinity is not actually a number. Infinity is just a concept, so it's not really a number. You can intuitively use direct substitution with infinity. And this all revolves around the concept of some finite number such as 1 over infinity. You're going to run into this a lot, and it doesn't have to be a 1 in the numerator. It's just any finite number in the numerator with an infinity in the denominator. So remember, a limit is what a function is doing near a point. So this just means, what is this overall fraction doing when you have a really, really big number in the denominator? Well, if you have a really, really big number in the denominator, you have a really, really small number overall. So, in short, a finite number over infinity can be approximated as 0. As the denominator gets larger and larger, the overall fraction is going to become smaller and smaller and approach 0. So what we're going to do is we're going to find each of these limits algebraically, and at the same time, we're going to determine if there are any horizontal asymptotes. So for this first one, I am going to split up the sum inside of this limit into the sum of two separate limits. So I'm going to separate this into the limit as x approaches negative infinity of 2, plus the limit as x approaches negative infinity of 10 over x squared. And then I'm just going to take one limit at a time. Now, the limit of a constant is still itself, even when you're involving infinity. So this limit right here is still going to come out to 2. And then for the next one, again, I'm going to just show the direct substitution because just so you have something to see, because this is a video lecture. If you were to, quote, direct substitute infinity, you would get this. Now, a negative number squared is going to be a positive number. So negative infinity squared is still a really large number infinity. 10 over an infinitely large number infinity, this can be approximated as 0. So 2 plus 0 gives us a final limit of 2. So what I want you guys to do is I want you guys to pause the video and try the next one. Okay, so for the limit as x approaches infinity of 2 plus 1 over x, I'm going to once again separate the sum inside of this limit and take the limit one part at a time. So I have the limit as x approaches infinity of 2 plus the limit as x approaches infinity of 1 over x. Limit of a constant is still itself, so that limit comes out to 2, plus 1 over a really large number infinity is a really small number close to 0, gives us a final limit equal to 2. Now, remember that squeeze theorem that we covered in a couple videos ago that you probably wanted to forget about? You can actually use the squeeze theorem for limits at infinity as well. So what we're going to do is we're going to use the squeeze theorem to evaluate this limit. Now, I see a sum inside of this limit, which is just going to complicate things. So I'm going to split up the sum inside of this limit into two separate limits just to make things a little bit easier. So I have the limit as x approaches infinity of 5 plus the limit as x approaches infinity of the sine of x all over, I'm sorry about that, I don't know why that popped up, the sine of x over the square root of x. Now, for this limit, as x approaches infinity of 5, limit of a constant itself, we know what that limit's going to come out to. Now, here's the problem with the limit as x approaches infinity of sine x over root x. If you were to direct substitute infinity, is sine of x doing anything in particular as x gets larger and larger? Is sine of x approaching anything as x gets larger and larger? No, it is, sine of x is forever going to oscillate between -1 and 1 forever and ever and ever, no matter how big your x is, over infinity. Square root of infinity is still infinity. So this is just all kinds of indeterminate if we were to direct substitute. So the limit as x approaches infinity of sine x over x, this is the part that is going to need the squeeze theorem. So I'm going to focus on that, and then I'm just not going to forget about this constant over here. So let's start with the part that is actually bounded. Sine of x is always bound between -1 and 1. And we're going to use this to figure out what two functions sine x over the square root of x is strictly bound between. So I'm not actually looking at the sine of x. I'm looking at the sine of x over the square root of x. So I'm going to take this inequality and I'm going to divide all three parts by the square root of x. So I have -1 over the square root of x. Then in the middle I have sine of x over the square root of x. And then on the right I have 1 over square root of x. Then I'm going to take the limit as x approaches infinity of all three parts. So I have the limit as x approaches infinity of -1 over the square root of x. Then I have the limit as x approaches infinity of sine x over root x. Then on the right here, I have the limit as x approaches infinity of +1 over square root of x. And remember, if you were to direct substitute infinity, a finite number over a really large number is a really small number close to 0. So -1 over the square root of infinity is still infinity because the square root of a large number is still a large number. So this limit comes out to 0. I'm going to leave the middle alone because that's what we're trying to figure out. And then for this limit on the right, +1 over the square root of infinity is still 0. So because the two outer limits came out to the exact same, and sine x over root x is strictly bound between these two functions, -1 over root x and +1 over root x, and because the outside limits came out to the exact same thing, that means the inside limit as x approaches infinity of sine x over root x is also equal to 0. So this limit over here came out to 0. This limit comes out to 5. So overall, your final answer, your final limit is equal to 5. Now, with limits at infinity of both power functions and polynomials, polynomials do not have any sort of horizontal asymptotes or really asymptotes of any kind. So the limits at infinity of polynomials and power functions are all going to be infinite. Whether they're positive infinity or negative infinity all depends on both the power and the leading coefficient. So for this first one, if you have an even power function, such as x squared or x to the 4th, x to the 6th, if you have an even power function, then it doesn't matter whether you take the limit as x approaches positive infinity or negative infinity. That limit is always going to come out to positive infinity for an even power function. Now, if you have an odd power function, if you take the limit as x approaches positive infinity, you'll get positive infinity. If you take the limit as x approaches negative infinity, you will get negative infinity, because a negative number raised to an odd power is negative. And then, if you have the limit as x approaches either positive infinity or negative infinity of a finite number such as 1 over x to a certain power n, or if you have the limit as x approaches infinity of x to the power of a negative n, it doesn't matter. A finite over some sort of really large number, x to a power of a really large number is still a really large number, you are going to get 0. Now, if you have a polynomial, the limit as x approaches either positive infinity or negative infinity is going to come out to one of the infinities, positive or negative. Which one it comes out to depends on the degree of the polynomial and the sign of the leading coefficient. So for these next two, we have the polynomial negative 2x cubed plus 3x squared minus 12, and we're taking the limit as x approaches positive infinity. So remember, for extremely large values of x, we're talking x equals 10 million, 1 billion, for extremely large powers of x. Which of these three terms is going to increase the fastest? Well, the leading term here, this cube term, is going to be increasing the fastest because a cube term is going to increase faster than a squared term, and that constant's just not really going to matter after a while. So the leading term here is what really determines the behavior of the function as x gets larger and larger. Now, if you take a positive number and you cube it, you get a positive number. However, it is always going to be multiplied by this leading coefficient, negative 2. So a positive number times a negative number is always going to come out negative. So the limit as x approaches infinity of this polynomial is actually going to be negative infinity. Because a positive number cubed is positive, but times a negative 2 will always come out negative. Now for the next one, we're going to take the same polynomial, but this time we're going to take the limit as x approaches negative infinity. So again, as x grows larger and larger in magnitude, the leading term is going to be increasing faster than the other two. So the leading term will pull on the end behavior more than the other two terms. Now when you take a negative number and you cube it, a negative number cubed is negative. And then it is always being multiplied by this negative leading coefficient. So the negative leading coefficient times a negative number cubed is going to give you positive infinity for this limit. So for polynomials, always look at the degree and the leading coefficient. Now, when you're finding a limit at infinity algebraically, and you have a rational function or any other sort of function that involves a fraction, you're going to be seeing this a lot. Infinity over infinity. Infinity over infinity is not equal to 1 because infinity is not a number, it's more of a concept, so that rule doesn't apply. So infinity over infinity is actually another indeterminate form. It's similar to 0 over 0, but it's not treated the same as 0 over 0. It does not mean that the limit does not exist. It does not mean that the limit equals infinity. It just simply means that you need to do more work to simplify it. Now, unlike 0 over 0, it's not a matter of a common factor that's not being canceled out. The issue with the infinity over infinity is it means that both the numerator and the denominator are increasing without bound and without restriction. So no amount of factoring or rationalizing is going to help you with infinity over infinity. So the techniques that you use to deal with 0 over 0 are not going to apply to infinity over infinity. So infinity over infinity has its own set of techniques to deal with it. So if you get infinity over infinity after an initial direct substitution, that means it is indeterminate and you need to simplify it. Now, we are going to revisit infinity over infinity a little bit later in the course, so there is more than one way to deal with this. But when the numerator and the denominator both involve polynomials, one thing that you can do at this point in the course is to divide every single term in the numerator and denominator by the highest power of x. Remember that any finite number over infinity is approximated as 0. So what we're going to do is we are going to find this limit here. So if you do an initial direct substitution, 3 times infinity plus 2 is infinity, over infinity squared minus 1 is infinity. So we have an infinity over infinity. No amount of factoring is going to help here, and I promise at this point in the course, here in Chapter 2, infinity over infinity can be dealt with by dividing every single term on the top and bottom by the highest power of x. So that's what I'm going to do. The highest power of x that appears here is x squared, so I'm going to divide everything by x squared, and you can do that as long as you do this to every single term on both the top and the bottom. So I'm going to have 3x over x squared plus 2 over x squared over x squared over x squared minus 1 over x squared. Then I'm going to simplify my powers as much as I can. Notice I haven't dropped the limit notation because I'm not actually taking any limits right now. I'm just simplifying this in a way that I can work with. So that x will cancel with one of those x's there, giving you 3 over x. Plus 2 over x squared is not going to simplify anymore. X squared divided by x squared is 1. And then minus 1 over x squared. So then I'm going to direct substitute infinity again. So I have 3 over a large number infinity plus 2 over a large number infinity squared divided by 1 minus 1 over infinity squared. Any finite number over infinity can be approximated as 0. So 3 over infinity, 0. Plus 2 over infinity squared, 0. Divided by 1 minus 1 over infinity squared is 0. Giving us 0 over 1. 0 divided by 1 is 0. So this limit came out to 0. Now, tying this back to horizontal asymptotes, we just took a limit as x approaches infinity, and we got a real number, 0. Because we took a limit as x approaches infinity and we got a real number, that means that there is a horizontal asymptote. Specifically, there is a horizontal asymptote at the line y equals 0. So, if you want to try this one before we get started, feel free to pause the video right now and then resume when you are done working. So for this next one, we're going to, again, if you direct substitute, you're going to get an infinity over infinity. So in order to fix this, remember, at this point in the course, there's only one way to deal with this. It's to divide every single term on top and bottom by the highest power of x. So the highest power of x that appears here is x to the 4th. So I'm going to divide every single term by x to the 4th. So I have 40x to the 4th divided by x to the 4th plus 4x squared divided by x to the 4th minus 1 divided by x to the 4th. All over 10x to the 4th over x to the 4th plus 8x squared over x to the 4th, and then plus 1 over x to the 4th. And then I'm going to simplify my powers as much as I can. So I have limit as x approaches infinity of, those are going to cancel out, leaving you with 40, plus that simplifies to 4 over x squared, minus 1 over x to the 4th doesn't simplify anymore. Then in the denominator, those cancel out, leaving you with 10. Plus, that simplifies to 8 over x squared, and then that last term's not going to get any better than that, so plus 1 over x to the 4th. So then we're going to direct substitute again. Any finite number over infinity is approximately 0. So we have 40 plus 4 over infinity squared minus 1 over infinity to the 4th divided by 10 plus 8 over infinity squared plus 1 over infinity to the 4th. So that will leave us with 40 plus 4 over infinity squared is 0 minus another 0 divided by 10 plus 0 plus another 0, leaving us with a final limit equal to 4. So because we just took a limit as x approaches infinity and we got the real number 4, That means we have a horizontal asymptote. Specifically, we have a horizontal asymptote at the line y equals 4. And then for this last one, if you were to direct substitute infinity, you are going to get an infinity over infinity. So again, I did promise at this point in the course, there's only one way to deal with this. So what we're going to do is we are going to divide every single term on the top and bottom by the highest power of x. Highest power of x that appears here is x to the third. So I have this x to the third divided by x to the third minus 2x over x to the third plus 1 over x to the third. Then we're going to divide that by 2x over x to the third plus 4 over x to the third. All right, so then let's simplify our powers. So x cubed over x cubed is 1, minus that next term simplifies to 2 over x squared, and then we've got this plus 1 over x cubed. Then in the denominator, 2x over x cubed simplifies to 2 over x squared, and then we have plus 4 over x cubed. So then let's direct substitute infinity. Any finite number over infinity can be approximated as 0. So we've got 1 minus 2 over infinity squared is going to give us 0, plus 1 over infinity cubed is 0. Divided by 2 over infinity squared is 0, plus 4 over infinity cubed is 0, giving us 1 over 0. Remember, a limit is what is happening near a point, not at the point. 1 over a really small number close to 0 is approximately infinity. So this is an example where we just took a limit as x approaches infinity and we got infinity. Infinity is not a real number. When that happens, because this is not a real number, that means that there is no horizontal asymptote. So for this next one, I know that the denominator does involve a square root, but there are polynomials that are involved in both the numerator and denominator because there is a polynomial inside of that square root. So if we were to take the limit as x approaches positive infinity of this function, I mean, I think it's obvious you will get infinity over infinity. Now, here's the thing about square roots. You can't take something that is in a square root and then just divide it by something that's not in a square root and expect it to simplify. Something like this would not be able to simplify very much at all. The only way that you can actually divide something that is inside of a square root by something and have it simplify is if they are both inside square roots. Because if you have a square root on the top and the square root on the bottom, you can condense it into the square root of the entire fraction x over y. So we're going to tackle this in the same way, just keeping in mind that for the square root in the denominator, we need to divide every single term in that square root by another square root. So the highest power that appears here looks at first glance to be x to the sixth. But this x to the sixth is actually inside of a square root. The square root of x to the sixth is actually x cubed. So in reality, the highest power of x here is actually x cubed. So here's what we're going to do. We are going to divide every single term in the numerator by x cubed. So we're going to take that entire numerator and we're going to divide it by x cubed. Then in the denominator, I'm going to divide the denominator by the square root of x to the sixth. These two are the exact same thing. We're not dividing the numerator and the denominator by different things technically. We're still technically doing the same thing to the top as we are to the bottom. I'm just writing that x cubed in the denominator in such a way that I will be able to simplify it with the square roots. So everything that's not in a square root will get divided by x cubed. Everything that is in a square root will get divided by x to the sixth. And since they're technically the same thing, we're not breaking any mathematical rules here. Also, our highest power is technically x cubed. When we cube a positive number, we end up with a positive number. So we're going to divide every single term by positive x cubed. I wasn't making a big deal of this before because, as you notice for these last three examples, we were all sticking to positive infinities. We're going to start getting into negative infinities next, and we'll need to start talking about negatives. But for now, we're going to divide by everything by positive x cubed. So here we go. We've got the limit as x approaches infinity of 10x cubed over x cubed, and then minus 3x squared over x cubed, and then plus 8 over x cubed. Then we're going to take everything inside that square root in the denominator, and we're going to divide it all by x to the square root of x to the 6th. So we have 25 x to the 6th over x to the 6th. And because these were both inside square roots, we can combine two square roots that are being divided into the square root of one fraction. So I'm just going to combine those all under one square root. Then plus x to the 4th over x to the 6th, and then plus 2 over x to the 6th. And then I'm going to simplify this as much as I can. So that will give us, those cancel out, leaving you with 10. Minus, that simplifies to 3 over x, and then plus 8 over x cubed. Then in the denominator, those two are going to cancel out, leaving you with 25. Plus, that'll simplify to 1 over x squared, and then plus 2 over x to the 6th. And then we're going to direct substitute infinity, remembering that any finite number over infinity can be approximated as 0. So we've got 10 minus 3 over infinity is 0. Plus 8 over infinity cubed, 0. Divided by square root of 25, plus 1 over infinity squared, 0. Plus 2 over infinity to the 6th, 0. Then we have 10 divided by the square root of 25 gives us 2. So our final answer is equal to 2. Remember, tying it back to horizontal asymptotes, is there a horizontal asymptote? Yes, because we just took a limit as x approaches infinity and we got the real number 2. That means we do have a horizontal asymptote at y equals 2. Now we're going to take that exact same function, and this time we're going to take the limit as x approaches negative infinity. So for x approaches negative infinity, this is going to be a little bit different. Now, our highest power of x is still going to be x cubed. However, a negative number cubed is negative. So the highest power of x when x is negative infinity is actually going to be negative. So what I'm going to do is I'm going to divide every single term in the numerator actually by negative x cubed. Now, because you can't take the square root of a negative, and negative raised to the 6th power is a positive anyway, I am still going to stick to dividing the denominator by the square root of x to the 6th. So it's going to be a very similar idea, but we're going to have a few more negatives in the mix here. So we have the limit as x approaches negative infinity of 10x cubed divided by negative x cubed minus 3x squared divided by negative x cubed plus 8 over negative x cubed. Then divided by, denominator is going to be basically the same, 25x to the 6th over x to the 6th plus x to the 4th over x to the 6th plus 2 over x to the 6th. And then I'm going to, not only simplify my powers, but I'm also going to simplify the negatives and positives as well. So those will cancel out, but 10 divided by negative 1 is actually negative 10. Negative divided by a negative is a plus 3 over x. And then positive divided by a negative is actually a negative 8 over x cubed. And then the denominator just simplified the exact same as it did on the last problem. So we've got 25 when those cancel out, plus 1 over x squared, plus 2 over x to the 6th. So then when we direct substitute infinity, we're going to get negative 10 plus 0 minus 0. divided by the square root of 25 plus 0 plus 0. Negative 10 divided by the square root of 25 is negative 2. So because we just took a limit as x approaches one of the infinities and we got a real number, there's a horizontal asymptote at y equals negative 2. Now, horizontal and vertical asymptotes are not the only types of asymptotes that exist. For true rational functions, which is one polynomial divided by another polynomial, not like this situation where we've got square roots involved, one polynomial divided by another polynomial. You can have horizontal asymptotes, you can have vertical asymptotes, but some rational functions also have what are called slant asymptotes. And while the process to finding slant asymptotes actually involves no calculus, the reason why that slant asymptote exists involves calculus. So we're going to first take the limit as x approaches infinity of this function. Now, an initial direct substitution doesn't give you infinity over infinity. So if you were to divide both the top and the bottom by x squared, I will let you guys do that on your own, but if you were to divide both the top and the bottom by x squared, you would get the limit as x approaches infinity of 2 plus 6 over x minus 2 over x squared over 1 over x plus 1 over x squared, which when you direct substitute in infinity, you would get infinity. So what that means, when you take the limit as x approaches infinity and you get infinity, there's no horizontal asymptote. Let's take a look at the actual function and figure out why. So yes, both the numerator and the denominator are increasing without bound forever and ever. That's why we got the infinity over infinity. But the numerator and the denominator have different degrees, so they're not increasing at the same time. They're just both increasing forever and ever. So the degree of the numerator is actually 2. The degree of the denominator is 1. So which of those is increasing faster? Well, a squared term is going to increase faster than a linear term, so the numerator is going to increase faster than the denominator. Because the numerator is increasing faster than the denominator, that is why this limit came out to infinity, because the numerator will become infinity faster than the denominator. So overall, that means that the y-coordinates are just going to increase without bound forever and ever, and there is no horizontal asymptote. However, the degree of the numerator happens to be exactly 1 higher than the degree of the denominator. So this is going to happen any time that the numerator is greater than the denominator, but when the degree of the numerator is exactly 1 higher than the denominator, you're going to have a slant asymptote. And the process to finding slant asymptotes is actually polynomial long division. So what I'm going to do is I'm going to just divide these two polynomials using polynomial long division, and I'm going to write my quotient and remainder as a mixed number. If you don't remember polynomial long division, here's a quick recap. We're going to put the 2x squared plus 6x plus 2 in, minus 2 in the division box, and then we're going to put x plus 1 outside the division box. Compare first term to first term. What do you multiply x by to turn it into 2x squared? Well, you multiply that by 2x. We're going to multiply and distribute, so 2x times x is going to be 2x squared. 2x times 1 is going to be plus 2x. Put parentheses around it and subtract them. 2x squared minus 2x squared is 0. 6x minus 2x is 4x. Then bring down the minus 2 and compare first term here to first term here. So what do you multiply x by to turn it into 4x? Well, you multiply it by 4. So then I'm going to multiply 4 to the entire divisor. Don't forget to distribute. So 4 times x is going to be 4x. And then 4 times 1 is plus 4. Parentheses and subtract. 4x minus 4x is 0. Negative 2 minus 4 is negative 6. And that is going to be our remainder. So if you were to write this as a mixed number, it would be your quotient, 2x plus 4, plus the remainder, so minus 6, over the divisor x plus 1. So we're going to use that to determine the slant asymptote for f of x. So slant asymptotes, they're also going to involve limits as x approaches infinity. So I'm going to take the limit as x approaches infinity again of 2x plus 4 minus 6 over x plus 1. Remember, this isn't a new function. I've just rewritten it so that the quotient and the remainder are written as a mixed number. And yes, this limit is still going to come out to infinity. However, if you take a look at this fraction over here, what will this fraction become as x gets larger and larger? Well, we're going to have 6 over infinity, so this entire remainder over here is actually going to approach 0 as x gets larger and larger. So what will happen as x gets larger and larger is the remainder is just going to kind of go off to 0, and the function is going to behave more and more like its quotient, 2x plus 4. So it will take on the behavior of 2x plus 4, and it will be indistinguishable from its slant asymptote, y equals 2x plus 4. So while the process for finding a slant asymptote is just polynomial long division, and your quotient is actually the slant asymptote, the reason why this is a slant asymptote involves calculus. So your slant asymptote is your quotient, y equals 2x plus 4. And remember, these happen when the degree of the numerator is exactly 1 higher than the degree of the denominator. So just kind of wrapping all of that up, for rational functions, you have a polynomial p of x in the numerator and a polynomial q of x in the denominator. And the degree of the numerator is m, and the degree of the denominator is n. When the degree of the numerator is less than the degree of the denominator, that means y equals 0 is going to be your horizontal asymptote. When the degree of the numerator is equal to the degree of the denominator, the horizontal asymptote is the ratio of the leading coefficients, so the leading coefficient of the numerator over the leading coefficient of the denominator. When the degree of the numerator is higher than the denominator, there is no horizontal asymptote. And when the degree of the numerator is exactly 1 higher than the denominator, there's no horizontal asymptote, but there is a slant asymptote. Now let's talk about a couple of these other functions before we kind of wrap this up. We talked briefly about trig functions, we talked about polynomials, we talked about rational functions. Let's take a look at the transcendental functions, which is e to the x and its inverse natural log of x. And if it helps, you can always draw a graph, and you can always use a graph for each of these. So starting with the limit as x approaches infinity of the exponential function e to the x. Well, if you direct substituted infinity, you would get e to the power of positive infinity, which, e to a really large number is still a really large number, approximately infinity. And e to the power of a positive exponent is a positive value, infinity. Now for the limit as x approaches negative infinity of e to the x, well, if you were to direct substitute infinity, you would get e to the power of negative infinity. Negative exponents can always be written in denominators, so this can be written as 1 over e to the infinity. E to a power of a really large number is still a really large number. 1 over a really large number infinity is approximately 0. So if you remember the exponential function e to the x, it actually looks something like this. It does have a horizontal asymptote here at y equals 0 at the x-axis. If you remember this, the exponential function has a horizontal asymptote at the x-axis. So if the limit as x approaches just one of the infinities comes out to a real number, it has a horizontal asymptote. Even though the limit as x approaches infinity equaled infinity, it doesn't matter. As long as one of the limits at infinity comes out to a real number, there is still a horizontal asymptote, and it still counts. So then for the next two, if we're taking the limit as x approaches infinity of e to the negative x, if we direct substitute infinity, we get e to the power of negative infinity, which we just said approximates as 0. Then for the next one, for the limit as x approaches negative infinity of e to the negative x, we will get e to the power of negative infinity, which is e to the power of positive infinity, which is a really large number, infinity. And if you remember the graph of e to the negative x looks something like this. So it still has a horizontal asymptote at the x-axis, y equals 0, and these two limits are reversed. Now for its inverse, so the natural log of x, if you might remember the natural log of x, its graph looks something like this. It is the, ignore that little glitch right there. So just ignore this. It is the inverse of the exponential function. So for the limit as x approaches infinity of the natural log of x, well, this is a very slow increase, but it is still increasing. So as x gets larger and larger, natural log of x is still going to grow larger and larger without restriction and without bound. Even though it's a really slow increase, it doesn't matter. The y-coordinates are still increasing without bound as x gets larger and larger, so this limit equals infinity. Now you might notice for the next one that we did not take the limit as x approaches negative infinity. Because remember how the exponential function can never give you a y-coordinate that's negative? For its inverse, it's the domain of the natural log of x is actually all x's that are greater than 0. Meaning you cannot take the log of a negative number and you cannot take the log of 0. So because we can't take the log of 0 or a negative number, we didn't even look at the limit as x approaches negative infinity because there is no graph on the negative side. I mean, there's nothing over here. Also, the reason why we're taking the limit as x approaches 0 from the right is because this graph only exists to the right of 0 because you can't actually take the log of 0. So this graph only exists from the right. So we're just going to look at this limit from the right. Now, as x gets closer and closer to 0 from the right, the y-coordinates are going to decrease forever and ever without bound. It's never actually going to reach the y-axis. This has a vertical asymptote at the y-axis, x equals 0. So the limit as x approaches 0 from the right is actually negative infinity. If you remember the definition of a vertical asymptote from the last video, we just took a limit as x approaches a number and we got infinity. So that means x equals that number is a vertical asymptote. So that means natural log of x has a vertical asymptote at the line x equals 0. All right, so that was it for limits at infinity. You might notice that there were some overlaps with infinite limits, so there can be some overlap, but limits at infinity deal with horizontal asymptotes and also slant asymptotes. So thank you all very much for watching, and I will see you all in the next video for continuity. Bye-bye.